Hello everyone, my name is Ruimin Chen. I'm a PhD student from Penn State Industrial Engineering. Today, I would like to talk about heterogeneous recurrence analysis of disease-altered spatial-temporal patterns in multi-channel cardiac signals. This work is done in collaboration with my advisor, Dr. Hui Yang. First, I would like to start with motivation. Based on the survey data, heart diseases are one of the leading causes of death in the United States. The number of heart attacks occurred in the US each year is approximately 800,000, which means that every day, around every 40 seconds, a person in the United States will suffer from the heart problem. So now when a patient goes to the hospital, the doctor usually obtains the electrocardiogram or ECG for patient's heart activity. ECG monitors the heart from 12 different directions, as you can see from here, which will generate a good amount of data. So these days, some researchers and doctors started to use the vector cardiogram or VCG to look at patients' heart activity. So instead of those 12 directions, VCG only monitors the patient heart from 3 different directions. This X1D, those 3 orthogonal directions, so which will significantly decrease the amount of data that we obtain. And in this study, we want to focus on the VCG data. Before going into the detail, I want to first introduce the recurrence theorem. The recurrence theorem, like the word recurrence itself, is about something happen and happen again, which is exactly like our heartbeat. Our heartbeat cycle repeats again and again. So here we have 3 different VCG signals, X, Y, Z, from those 3 orthogonal directions. And then we first embed them into the space. We can see there is a space trajectory here. The recurrence theorem indicates that the trajectory will eventually reappear at the neighborhood of the former state. So here, as you can see, we have a sphere here indicating the epsilon neighborhood. And in the formula that is showing here, the R stands for the recurrence matrix, and then I and J denotes 2 different states. So here, if the trajectory reappear in this epsilon neighborhood, then we say we have a recurrence behavior here, and then we will put a black dot on the corresponding place in the recurrence plot. Where on the other hand, if the trajectory doesn't go through it, we don't do anything on the recurrence plot. We will just leave it white because we don't have any recurrence behavior or recurrence pattern at the corresponding time. So after analyzing every data that we have in the signal, we will get a recurrence plot. Something look like this. And then the pattern on the recurrence plot indicate different recurrence behaviors. For example, the single dots, the vertical lines, and the diagonal lines indicate small-scale structures. And then the homogeneous patterns, periodic patterns, and disrupted patterns, for example, they will show some large-scale structures. And further, we can use those statistical features. For example, what we have here are the recurrence rate, the determinism, the linearity, and entropy, those different statistical features to quantify the patterns, recurrence pattern from the recurrence plot for further analysis. However, as the system is becoming more and more complex, and also our heart itself is a very complex system, so there actually might be more than one type of recurrence behavior exists in the system. So for example, as we can see, this time series data showing on the slide, at least we will have 2 types of different recurrence behaviors. The first one is showing in the red circle, and the second type is showing in the green circle. So in our study, we want to focus on those different types of recurrence behaviors, and we want to quantify the heterogeneous recurrence behaviors in the data that we have. So in this study, we propose a heterogeneous recurrence analysis to study the VCG signal, and the procedure is showing on the slide here. And first, what we need to do is we need to do the state space segmentation for our embedded trajectory. So here we use a multidimensional indexing approach to partition the m-dimensional space by subdividing it to the two to the power of m subregions. So for example, here we have the heart trajectory from two patients here. And then as you can see, we are subdividing both of them into 8 subregions. And after putting them, or after dividing it into the region, the next step is we need to do the labeling. So for example, let's say we have a time series data from A to M here. So as you can see, the data A to C falls into this M1. So what we are doing here is we are labeling 3 of them to M1. And then D, E, F, 3 of them falls into M2. And then we are just labeling them to M2. And then we are just gonna do this for all the data that we have in the signal. And after this, we will see some transitions between those states in the labeled or in the index data that we have. For example, we will have transitions from M1 to M2, or we will have transitions from M6 to M7 to M8. And those are indicating different recurrence behaviors. So after getting that we will have different recurrence behavior, the next question the question we ask ourselves is how we can study those different types of recurrence behavior. So to quantify the heterogeneous recurrence behavior, so before that we have to do one more step. Here we first use a fractal representation to plot the states. So here we calculate the Ifs address for each point in the signal. So let's say we have a embedded, or we have a label signal look like this. And then we start from the first state that we have. So for example, if our first data falls into the state 3, and then when we calculate the Ifs address based on the formula that's showing here, we get the corresponding Ifs address equals to around negative 0.7 and positive 0.7. So here we, this point is around, it's something around here. So, and then we put this point on the plot that we have. And then we calculate the Ifs address for the second one, the second data that we have. And then we keep doing this for all the data that we have in our signal. So at the end, we will get a fractal representation looks like this. So here, note that the two states can have the same address if and only if they share the same categorical variable and all of their previous states are the same. Because here we have n-1 here in the formula. So therefore, the Ifs address is unique. So that's how we can distinguish there exists heterogeneous recurrence behaviors. So after we plot that, or after we represent that in this way, and then next question is going to be how we're going to use this, or how we're going to quantify that, how we're going to change this plot to some numbers. So here at the last step, we extend the traditional recurrence quantification, which was trying to quantify the homogeneous recurrence behavior in the system, to the heterogeneous recurrence quantification. So here we extract 5 different quantifiers from the system that we have, namely heterogeneous recurrence rate, heterogeneous mean, heterogeneous entropy, heterogeneous liminarity, and heterogeneous trapping time. So we propose those 5 different quantifiers for the quantification. Then we validate and evaluate our proposed methodology first on a simulation data. Here we generate 2 attractors. One of them is Lorentz attractor, and then the other one is Rockledge attractor. So here we extract both the traditional homogeneous recurrence quantifiers and also the proposed heterogeneous recurrence quantifier from the 2 systems. And then we summarize the quantifiers into a Hotelling t-square statistics. So here, as you can see on the y-axis, and then y-axis is the Hotelling t-square statistics. And then as we can see on the right side, the result part, the heterogeneous recurrence quantification can capture the difference between those two systems. However, on the other hand, the traditional recurrence analysis is focusing only on the homogeneous recurrence behavior, and it cannot capture the difference between those two systems because their ranges are very similar. And after our simulation study, finally, we used the proposed methodology to analyze the real-world VCG data. So here we extract the VCG data from the PTP dataset from PhysioNet, one of the biggest data, open source online data about the medical data. So here in our data, we have VCG signals from patients in two groups, and one of them is the healthy control, and the other one is the MI group. So this group is the patient that don't have any heart disease, and the MI group will be the patient with different heart problems. So here we use one patient from the healthy group and one patient from the heart disease group to show the procedure of our analysis. So as you can see, the heterogeneous plot shows different patterns from two patients. And also the fractal representation shows there are some different recurrence behavior exists in their VCG signals. And also the quantification show there are significantly differences between the two groups. So here, the blue one indicates the patient with heart disease, and then the red one shows the patient, the healthy patient. So after the quantification, we further perform a classification study to see the performance of our heterogeneous recurrence quantification. So compared to the two previous studies from our group, we can see that the performance of the proposed methodology, the analysis, the performance is pretty good. So in conclusion, in this study, we characterize heterogeneous recurrence behaviors and patterns in the VCG data, and we quantify the heterogeneous recurrence features. And in summary, a fractal representation of VCG signals is designed to capture the salient patterns of heterogeneous recurrence behaviors. And a set of heterogeneous recurrence quantifiers is calculated to characterize and measure different patterns. And then at the end, multivariate predictive model considered the joint variation of quantifiers for the identification of MIs. And those are the referencing papers. And at the end, if you have any questions, please see our contact information here. And thank you very much.